What is the age of the discontinuity? Is the same of the main central thrust. For example, Catlus in 2001 and 2018 considered an age of the main central thrust between 25 and 6 million years. So falling completely in the same time span of the HD. So we started to work in the field. Here we can see a picture of the Marciandi Valley. Here there is a South Tibetan detachment, the Chami detachment, and here the main central thrust, upper position, lower position, but you will see this afternoon by some students of Capital Parodial the exact position of the main central thrust in this valley. And then we found a very interesting shear zone close to Jagat, in this area, where we found beautiful myelonites with shear plane deep into the northeast, sense of shear top to the southwest, and we found also beautiful silimanite crystals growing along the shear plane. So with structural feature very similar to the HSD in western Nepal. So we checked also the deformation close to Chami detachment, and we went in the Nar Valley for a few kilometers, and we found beautiful kinematic indicators such as delta porphyroclast in this feldspar crystal, sigma type porphyroclast, and mica fish myosin leucogranite, but all these kinematic indicators point a top down to the northeast sense of shear. So at Chami we confirm the occurrence of the South Tibetan detachment system and not a thrust as proposed by Walters and Kohn 2017. And we made also some exploration in the Burikandaki Valley, and just in a similar village called Jagat we found a similar situation. So we can trace this shear zone across the two valleys in this position, in the middle part of the Greater Himalayan sequence. Here there is a South Tibetan detachment, and here is the main central thrust. To gain the age of the HD in close to Jagat and the age of the main central thrust, we selected 4 samples. One from the upper part of the Greater Himalayan sequence, one in the shear zone, one in the lower part of GHS, and one close to the main central thrust upper shear zone. They are myelonite gneiss, paragneiss, and migmatite gneiss, the sample 33. We investigated this sample to looking for monazite to gain the age of the shearing, and there we can see the sheared rocks at the outcrop, the scene section, and the scene section where under the optical microscope we detected the occurrence of a monazite. Then we checked the monazite under the electronic microscope to be sure not to confuse with other accessory minerals. We detected also the chemical zoning of monazite, and at the end we dated by uranium lead by laser ablation split system. That is a system that gives the age and also the chemical composition in the same place. That is very useful for this kind of investigation. Here you can see monazite under the electronic microscope, monazite after laser ablation with the holes, and chemical analysis of monazite showing a distinct composition between the core and the mantle for the yttrium contents. If we consider all the ages that we found in the monazite in the upper GHS and along the shear zone, we found very older ages in the yttrium poor core, indicating progressive metamorphism, because during progressive metamorphism, yttrium is concentrated in the garnet, whereas in the monazite, the yttrium is very poor. Differently, when we are in the electrolytic condition, with breakdown and resorption of garnet, all the yttrium is released in the system and is concentrated in the rims of the monazite. So if you use the core with poor yttrium and the rim with higher yttrium contents, highlighted by red color in this picture, we can detect the prograde and retrograde path, following the paper by Williams and Jurcinovic, Engi and others 2017. There are several papers demonstrating this relation, also by Matthew Cohn. And a similar but inverse behavior has been detected by the thorium. With thorium, you have high core thorium and low thorium rings in the same path. So if we put all the ages in this diagram, we can see that all the ages in between 40 million years and 27, 28 million years are related to prograde metamorphism, and usually these monazite are included in garnet or in biotite, so they have a structural position related to the prograde path, whereas the green line shows the retrograde path of the monazite. That is the ages recorded by the rims during the retrograde path of the PT path. So for the sample 33 and 90, the ages are very similar. Prograde path up to 25, 27 million years, and retrograde path up to 15, 16 million years. But the game is not over, because in the Kaligandaki we found also an older shear zone, the Kalopani shear zone, just in the upper position of the great Magellan sequence, shearing the unit 3 of the great Magellan sequence, and we found for this shear zone ages of exhumation from 41 to 30 million years. So the meaning is that we have several shear zones: main central thrust, HHD, Kalopani shear zone, South Tibetan detachment with a different kinematics, but the exhumation of the great Magellan sequence started from the upper part, then moved to the middle part, then to the whole part when the main central thrust was activated. So the mechanism is an in-sequence shearing mechanism, starting from the upper position, but at the time of activation, as we can see from this picture, the depth was close to 30 kilometers, because you have 10 kilobars of pressure. So we have the progressive activation of shear zone from the older one to the younger one, from the upper part to the lower part. So going to the conclusion, GHS is affected by a regional scale high temperature shear zone that separate the mid-crustal rocks from the upper part and the lower part. The HD was active before main central thrust, but in an upper structural position. HHD caused the shifting of the timing of maximum PT condition, reached in the angle in the future. The shift is of nearly 10 million years. There is 10 million years of time between the exhumation of the upper part and the lower part. And if consider all the timing of activation of the Kalopani, HHD, and the main central thrust, we suggest an in-sequence shearing of the formation for the exhumation of the greater Himalayan sequence. Okay, thank you for your attention.
And I would like to show you some of the problems we are facing with various types of geological field investigation in Nepal. And I think one of the key issues in Himalayan geology is mapping in detail. Due to the rugged nature of the mountains, as well as quite harsh climatic conditions, it is hard to do long field work. And also due to, I think, lack of time to spend in the field, we have been suffering from various kinds of maps. And the problem is very critical, because Now Nepal is going to develop its hydropower projects, roads, as well as other kinds of infrastructure. And the problem is very complicated. The geologists have put a lot of faults and as well as other geological structures, and the infrastructure developing institutions don't know how to read these maps, and they think our geological maps are equivalent to topographic maps, but they are not so accurate. Oh, the tectonic windows. I think the last 10 or 15 years, if we go through the literature, Himalayan literature, especially in Nepal and Sikkim, we will find many types of geological maps and cross sections. And sometimes it is quite, disappointing to be in the field and not to see any of these things mapped and depicted on cross sections. And I'm not trying to criticize anybody, but I would like to put forward the conditions what I found, and it is up to you to decide which is correct and which is wrong. This was, I suppose, the earliest geological map of Himalaya, Western Himalaya, between Nepal and India, the western part by Strachey. And interestingly, he showed Shivaliks, as you can see, and these lesser Himalayan and greater Himalayan sequences with intrusive rocks here, and other sequences. That time we didn't have thrust faults. Sorry. Yeah, it is his cross section. And we see that he shows some igneous rocks and very beautifully the dipping direction of beds and these amphibolytes in his cross sections. It was the first time when he put these beds and other things fully in the cross sections. Then came the map of 1933 and from 97 onwards, and the geology started emerging from this part, from northwest to east, and we could see some kind of mapping going on in Kuma, Simla area, and in Kashmir and in other parts. The first thrust sheets were put forward by Pilgrim and West, but later on, most probably they were not so much folded as they have shown here. But anyway, they were the first to show the thrusting in Simla area, and these cross sections, were made by making kind of recumbent folds, tightly folded structures within this area. And the same area was mapped recently. And here we see, this was the area they studied. Here we see the lesser Himalayan sequences here, the greater Himalayan sequences. And here we see granites and other acidic rocks ranging in age from Proterozoic to Paleozoic. So that is very interesting, because in Nepal we think that we have only Paleozoic rocks, igneous rocks in the high Himalayan sequence. But here, as well as in Almora, they have the Paleozoic rocks in the thrust sheets. They call it Zuto thrust sheet, others call it Chail or Ramgarh thrust sheet, but they are the same. This was the first window mapped by West near Simla, north of Simla in the Sutlej Valley. And he showed the window based on these stromatoliths, dolomites, some tertiary beds around here, and other mud slates and other things. So it was almost completely, covered by this thrust fault of basically Simla slates. Bertelsen made first cross section across the Himalaya, and interestingly, his work is so important because we could see he tried to show many faults and naps here, as well as south dipping structures near the industrial zone, which we call now industrial zone. So it is, I think, one of the very remarkable sections of the Himalaya. And here we see the windows. Yes. This was Hagen, who worked for more than 9 years here, and it is his sketch map of Hagen. And we see Darandura area, this is Bazam, this is Buriganga area, this is near Jumla, and here we see Kathmandu Valley, and this is east of Kathmandu, and Arun, and this is Tamil window. I would like to point out to one important fact here, that you see these authors starting from Hagen and earlier, you see they have shown the concentric nature of these dipping up beds. You see the beds really bend around, you see, here as well as here, and here is almost completely dipping in every direction, and it really windows are there. Not only the top, but within the window also these kind of structures were identified quite early, like here. This is the Hagen spectrum map, and we see the windows here and here, and of course you know this one Trishuli Valley, and this is another window, and here it's not very clear, and this is the Tamil window. One important point here is that Hagen thought this is something different from all other rocks, and he thought that that should be something different from these units, and probably he was right in some way. Then came Ganser's, Hyman Ganser and Ganser's work, and they clearly showed these windows in different parts, and they made these cross sections, and the Swiss zone is here, and we could clearly see large scale thrusting in the Himalaya from the cross sections made by Ganser and Hyman Ganser. It was Fuchs who made this quite extensive, field work, and then he mapped windows in Nepal and in India, in the east, and you can see the almost from Hagen, Ganser, and Fuchs, we come up with the present day geological map of the country. And look at the windows here, how they have interpreted. You see the structures here. The folding in the windows. Like Fuchs, this is Laford, who clearly show the MCT, more or less distinct structure, and the windows within this. And they also made some cross sections. So, like here, you see the MCT, Dana, and this section, and strongly folded, and there's a Pepin sequence and inverted metamorphic sequence south of Dana. But suddenly we have this map in 2008, which is entirely different from the MCT I just showed you. Just I will go back here and here. You see, here you see we have windows and the rocks, Klippen and others. Once we go back, we see now MCT has come far south, and those Searle and others, they talk about, there are other authors inside, they talk about the structural shading and many other things. Effectively, their MCT is the garnet isograph, though they don't like to call it like that. But the point is, all the earlier discussions I just made clearly showed that the rocks are not concordant. Actually, MCT will cross-cut our geological beds. If we follow this MCT, it will cross-cut all the geological beds. It will not be concordant to the foliation. And here, I'm sorry for poor quality. My main intention is to show which map you could prefer for your further work or research or hydropower project development. Here we have two parallel faults, MCT and Ramgarh thrust, going throughout the Himalaya here, Here we have along this MCT, along this, and no other thing is all belongs to the lesser Himalayan sequence, and MCT is somewhere here. Here we have very different situation. Here we have the MCT here, and no MCT in this part. So this kind of things are really troubling others, not only geologists, but other people who are working for other kind of work, projects. This map is somehow, we can see some structures. The most important thing I think is to show the geological stratigraphy and structure on the map. Otherwise, it is very difficult to really understand it. You see, they have shown Kuncha and other younger rocks around, and there is an antiformal structure passing through this, as you can see. And Hagen had shown this already, and you can see these are in the core of the antiform, where we have the windows. All these windows are within the core of the antiform. And not only the high Himalayan sequence or great Himalayan sequence is folded, but the lower units are folded as well. And it was seen by many others, and anybody can go and check it in the field now, even now. But unfortunately, this area has been in a big controversy. But if we walk through Gulchi and there is a road to Saptabesi, you will see Bengard slates coming from here, and continuously you can trace to Saptabesi. But the rate of metamorphism will of course change from slates to kyanite. So the problem is, if we put the MCT based on isograds or greater metamorphism, maybe we need to put somewhere like this. Or if we put the MCT based on other kind of criterion, maybe you can put the MCT somewhere here or here or here. Yeah, this is the cross section from Radhathura area. You can see several imbricates here, many of them inside, but the exposed ones are just one at the surface, but all are inside, But how to know that they are there? But here you see they're slicing the Kuncha formation into different, different bands. But this is the map by Khan from Department of Mines Geology from the same area. This one, this cross section is almost from the same area as this map. You see, there are deep strikes everywhere. He has made a meticulously accurate map. And you see, they are closed. They are all antiformal stacks. If you talk about this thin tectonics, there must be stacks, But we don't see north-dipping structures in this. And this quartzite band is coming like this here, and this is a tertiary bed here, which is actually moving somewhere here. And this map is incomplete because we are still working here. So that gives us a very different picture from the cross-section. And Fuchs, who mapped this area with Frank, this is his map. And again, we see the lesser Himalayan sequence, all are folded. Here you can see a lot of folds in it. And it is his cross-section, their cross-sections. They clearly show the folds in the lesser Himalayan sequence. This is, of course, the great Himalayan or high Himalayan sequence here. And they are all folded. But if we make them all dipping like the indicates, it will be quite difficult. Here, this map by Stocklin and others was based on about 18 topographic sheets that were mapped on a scale of 1:1 inch, and it is a compilation, and they have a western sheet as well. And this is not just a map of 1:1 million or 1:250,000 scale. It was based on many field data and from the aerial photo interpretation. So it is not just, and anybody goes to the field and just draws a line here or there and here, and everything, is something different. And it clearly shows that these rocks in the valley are above the gneissids and all other rocks, here. They are not below these, these rocks. The stratigraphy is this way. This is down and this is up, but not the opposite. They are not below and they are not above. That I will show you here. You see, but unfortunately, the same map prepared by the same government body has shown different names. Again, another confusion. You see, they have used the same map, but you see, if you look at the names here, formation names, they will be entirely different. My point is, what was the stratigraphic basis of that? Did they make stratotypes? Did they make stratigraphic sections from the area? Or if you pick up one name from here, another name from here, and one from here, and make a map, it will be very difficult. You must have a section, and then you have to follow stratigraphic code. Only then we can come up with a good, nomenclature. In that respect, this map is, I think, far better than this one. Again, go back to Hagen. We see this structure here. Very clearly, he showed that there is no fault in between. Even if, suppose we put a fault here, it will be an elder fault, or younger fault, because it will cross-cut the foliation. It can be older than the foliation itself. So, even if you try to put a fault around, it will be younger than the foliation. So, it must be a syncline and there must be a bridge. Gosai-Kun bridge. But, look at this section. From the same area, this is the Gosai-Kun bridge with so many slices, without any field data. That is the most intriguing one, for me. Because you see, this is our well-known area, Tamsen here, this is Palpa, here we have Sakai's map of Tokuoka and others, geological map of Tokuoka is here, Suraikola area's map is here, then we have the Sakai's map, 2 maps, we have done some work here, but if you look at these boundaries, they are all straight and vertical. And you see, the folds, so sharply put folds around. And this is the cross section. But I just want to compare this map with our maps. Yeah, this is the ediform I want to show you from Pokhara, which is clearly, you can see, this is, Pokhara is somewhere here, valley. You see, this is a clear-cut ediform here. That doesn't exist in the cross section. And look at this one. This is, I don't claim that this map is good. But what I want to tell you is, you see, the beds are really folded. They are overturned stromatolites, upside down, posing stromatolites. And they are really strongly folded, as you can see, from the boundaries. And it is just a sketch map. The real map was prepared, it took about 2 years to map it, and one took sheet of 1:50,000. But this area is this one. It's the same area. Kusma is somewhere here. You see, Kusma is here, you see. Kaligandaki Valley is this one. But Kusma is here. This is the Kaligandaki Valley. I don't know. Sakai's mapping of Kaligandaki Valley was remarkable. And he was an excellent, mapper. But this map is this, just this one. Look at this one. Is it anything similar? It's densely folded and, completely, tangled confusion is here. Look at this part. This part is this map. And their cross-section passes through this folded structure, and many clip pen here. You see, you can see 1, 2, 3 clip pen are here, and all are folded together. But that doesn't exist here. So, just an example, we do have imbricate folds and some back thrusts, like here. This is a pure back thrust. We can see here, and we see the back thrust here. Yeah, we can see the folded ones, structures around. Tight folding is seen. Yeah, you can see the tertiary beds just at the top, here, somewhere here. And if you compare this section with somewhat this one, They are totally different. Let's take a look at this central part where many researchers are working still now. Here you see, these are Technicak sequences which are below the MCT. Here the Technicak sequences are, here the Technicak sequences have been put below, but in reality they are not below, they are above, as you can see from this sketch. And here we have this cross section. This is the cross section from here. But we clearly see that there is a continuous sequence, and these are the granites here. Here, this Paleozoic granites folded ones, and it's a complete sequence. And Yonging is to the top. They are not overturned. So there is the MCT is really somewhere here. Somewhere here.
Professor Vital, can you summarize?
Yes, I'm going down. So I just want to show you the problem with the map manipulation. You can see they are trying to put a fault around this, but they are not able to do so. So they are trying to put a lot of, like a vertical fault here, they are making a syncline. But these are not, they are all doing mapping on this 1:1 million or 250,000 scale. Again, they want to put a fold here. That is absolutely impossible because we don't have such structures. So I just want to show you this window, tapestry window, and map by shading. He just put a, outer sequence thrust in it and made a balanced cross section. Recently we have worked in this part, and our work shows that these are all continuous things, and this is the core. In the granite, the tapestry granite is in the core, near the core. And these are all continuous beds without any such complications. And this is our section column, and these are the isographs. And of course, we found that they are beautifully, distributed isographs, and they are completely inverted without any doubt. But the isographs don't map structures. In conclusion, I would like to say that we need some more field work, and integrated approach with field and lab, and with a group of scientists can probably be the best way out of this kind of problem of mapping the windows in the Himalaya.
Ilmenite is formed near the shear plates, showing shear plates with kyanite and selenite. Whether it is a breakdown reaction of muscovite plus quartz give rise to orthoclase and selenite, how you can correlate whether it is a product of a prograde reaction or retrograde reaction.
Thank you for the question. We found the retrograde reaction because we can find silimanite after biotite and after kyanite. We have the silimanite as a stray shadow of kyanite, for example. So we have the quick metamorphism and the retrograde reaction.
In between, we do have these, these leucogranites and these myelonites and these things. So you mean to say that we have a shear zone between MCT and the STD, which is SD now?
I think yes. We published a paper in Health Science Radio this year, and I visited Zekil in 2006 maybe, and I found very strange because people put the med-central thrust in the very higher position, just as the enigmatites. So if you put the med-central thrust lower, just in the boundary between greater Himalayan sequence rock and less Himalayan rocks, you can have a shear zone in the middle, as some authors detected by similar investigation. So I think there is discontinuities. This one is a key matter. I don't remember the name because.
Another point is that Professor Valdia, he puts between MCT, his MCT in fact is Vectrita thrust. What he says, Munshiari thrust, then Vectrita based on the Brecken metamorphism, high grade metamorphism, then STD. So is it something, how do you take Vectrita as MCT or within MCT and STD?
Thank you for this question. This is just the topic that we try to answer in the last 2 years. We visited Gaval and we have investigation by Creta and Munziari. And for the by Creta, we found the ages from 11 to 6 million years by argon on white micas. And during the last trip, just 2 months ago, we were to Badrinath and we found a thick myelonite in between MCT by Creta and South Tibetan detachment. So I think it is possible to have such a discontinuity different from by Creta, and by Creta is more or less the main central thrust upward.
Okay, thank you very much. Nice presentation. New data from the Himalayas. Now the questions to Professor Vital.
I have some queries about these windows. Mostly in western part of Nepal, we see thrust sheets, very large thrust sheet. But whenever we go to the eastern part, then we can map the windows. So within these very short distance, this type of tectonic development, different type of tectonic development. So how can we interpret this tectonically? This is one my question. And second, we have several thrusts in lesser Himalaya. Say there is Tansen Klipe and Kapurkot thrusts. So these thrusts, how can we link the event of these thrusts when they were formed? Whether they were older than MCT or younger than MCT. So these two are my curiosities.
I think the first question is somehow related to the erosion of the mountains and the movement of the river valleys and the rivers. Hagen has made a map of the rivers of Bagmati, Karnali and others. According to him, it seems that river have subsequently changed their course. And instead of flowing from north to south, they start flowing to east or west. And due to the tectonic movement in the Mahabharata range or to the south of that. So probably it can be linked up with the tectonics, of course, and the erosion, and the thickness of the shivaliks exposed. To the east of Kathmandu, shivaliks become very thin. And in Bhutan, the lesser Himalayan rocks come or override the sediments. So probably due to that, I think the movement was different, thrusting movement was different, and erosion was there. And there was some tectonic activity at the front. That's why we have this kind of large scale erosion in the central part and no erosion of this thrust sheet in the east. A second question is, we have many implicate faults, of course, and duplexes, there is no doubt about that. And we have, their age is difficult to, constrain now, but most of them are post, the Miocene, because we have the Dumri like younger Miocene beds, they are involved in thrusting. And that could be quite young, even a few million years. But because in the shivaliks we have the implicates, so they should be quite young.
How to define a window? Tectonically, now there is stratigraphic problem, there is so many complications. So how exactly we should define now a window so that a uniform definition can be done for that?
Thank you. I think it's kind of dilemma. Either we must have a knowledge of stratigraphy or we must have a knowledge of structure, or actually both. If we don't work out stratigraphy, we cannot define any thrust or windows. In our case, luckily we have generally quite metamorphosed rocks of Great Himalayan sequence. And we have less metamorphosed rocks at the base. And we can trace out the metamorphosed ones quite, accurately. So we can see that under the high Himalayan or the Great Himalayan sequence, we have the windows. That's very, I think, a way of defining windows. And if there is an extensive erosion, then we'll have remnants of cliff. There are two of them in the Himalaya that I didn't discuss now. So, but for the, I think most important thing is to faithfully map the structures and the lithological units. If we don't map the lithological units faithfully and just rely on the other people's map, there could be troubles. Especially just recently in one hydropower project, one guy put the MCT and he used 1:1 million scale map, and his error was already 1 kilometer in 1 millimeters. That's too great for the hydropower projects. Another important point I would like to emphasize is that metamorphism was post-thrusting, as we are seeing in some part. So even the tertiary beds are metamorphosed, as Professor Sakai has shown in the windows. So don't take the metamorphism as the stratigraphic units. Metamorphism is very important, it is inverted, very fine, but we have to think of the protolith. You have to think of what was the rock before metamorphism. Then we can have the stratigraphic units more precisely, and then try to compare with existing stratigraphic units of other parts of Nepal. Thank you.
Yeah, one more thing is that, that's okay, and in Sikkim we have Rangit window.
Yes, sir.
It's a detailed, mapped in detail, what we have Proterozoic in the center, surrounded by Gondwanas, then MCT comes, and the whole thing is folded. So it is known as Sikkim dome. And there also a lot of complications are there, different maps are there. So I don't say that it is, the mapping is wrong or this, everything is okay. So that is a perfect window in the Sikkim Himalaya, which is accepted.
Yes, yes, like our Tapaji window, they are very similar. Thank you.
Okay, the invited lectures are there. So the first invited lecture, I invite Dr. Krishna Prasad Kapale. He will be speaking on an overview of metallic mineral resources of Nepal with special emphasis on potential iron prospects and their importance in national development.
So the topic is, I told you just now. So in this, my presentation is quite different. Before, because it is a review paper, so not specifically scientific papers, particular points. So mainly I will discuss about this revision of some general geology of Nepal, very short, by 2 slides I suppose, and metallic mineral resources and iron prospects in particular, or iron ore tribes, present status of iron ore deposits and prospects, national demand of iron ore and iron and steel import situation, and then the prospecting and mining license issued by the Department of Mines and Geology, investment opportunity, conclusion and recommendations. So, in introduction, Nepal Himalaya, the highest and youngest mountain in the earth, it terminates, it terminates towards eastern and western part in the Indus, and then eastern part of the Brahmaputra River, and this is the whole Himalaya, and it forms the syntextual bands in 2 places and become convex towards the south. Nepal Himalaya is almost 1/3 part of the whole Himalayan range, and then it lies in the collision zone between the Indian plates and the Tibetan plates. So in general sequence and say general geology of Himalaya, this morphogeotectonic, technically Nepal Himalaya can be divided into 5. Many of you are aware of it. From north to south, Inner Himalaya or Tibetan plates, higher Himalaya, lesser Himalaya, sub-Himalaya, and the Tarai plain or the Indo-Gangetic plains. Prominent linear structures, we'll go further ahead. I don't like to go detail in the further. So some nepe, clippe, faults and transfer faults are developed, and granitic intrusion of formation in the lesser Himalaya, and then tertiary in the higher Himalaya and the Tibetan terraces. So geological structure, geodynamics, granitic intrusion and metamorphism plays quite favorable geological environments for more than 500 occurrences in prospective deposit of over 63 minerals, commodity including more than 30 metallic minerals. So metallic mineral resources, minerals are the, everybody knows that the hidden treasure and non-renewable mineral resources which are the valuable asset of the country. So as per the Department of Mines and Geology published records, there is Nepal is fairly is now prosperous in metallic energy mineral as well as construction minerals. But on the other hand, there is no single metallic mines in operation at present. In spite of six mining licenses and 25 prospecting licenses are issued by the department. So, in the beginning, during the 1960s, Geological Survey of India, they have worked, and then followed by DMG, 1996 to present, and a lot of these union-funded mineral exploration development projects that has been worked and explored minerals in different parts and at different stages, mainly in the Lesser Himalaya and the Sub-Himalaya. Most part of the Higher Himalaya, as always, Tibetan is to remain virgin. So, such limited mineral exploration activities reveal that Higher Himalaya and the Lesser Himalaya regions are potential for metallic minerals like gold, copper, iron, silver, lead, zinc, nickel, tungsten, tin, etc., and barium, lithium, as well as beryllium and uranium, as well as even rare earth elements. Okay? Whereas Tibet tradition of Himalaya has potential for the radioactive minerals. So this is the metallic minerals. I made it simplified for about 17 minerals. So location and there, most of they are shown these metallic minerals over here. Now, knowing metallic minerals in Nepal's gold, we have the primary gold occurrences, 9 places in the 4 districts. Similarly, pressure deposits almost in all the major rivers which comes from the higher Himalayan side, and if you see the terraces in evaluation of the river beds, we can find the lesser gold. Similarly, silver mostly associated with the lead zinc, similarly copper 107 places in 30 districts, lead 54 places 70 districts, iron 91% location in 32 districts. So like that, so these are the minerals we have located in different parts of Nepal. So now specifically now I talk about the iron and its use and demand. Iron is the principal metals, as you know, used since long time and is still present. It is extensively used in all types of civil works, right? Civil construction work, and infrastructure development works to manufacture heavy machinery equipments, arms, mechanical and agricultural tools, then furniture, utensil, iron and steel products, etc. Present demand of iron and steel is around 10 million tons, all including this, and this trend is increasing. I'll show you later. Now, iron ore deposits are mainly, we have the ore, hematite, magnetite, limonite, and nearly some siderite. Iron ore deposits prospect of occurrence altogether, I told you before, 91 localities in 30 districts that have been identified and categorized them economic, sub-economic, and non-economic deposits. But many of them, they have not yet explored in detail, right? So you have to do a lot of work on that. Some of these are deposits where locally mined and smelted in different parts in Nepal since historic time, but not after 1964. After 64, there were some mines, but after that, no. And at that time, a small gun factory was established in 1863 based on Thoshe iron deposits. And in those days, Nepal was also exporting copper and iron to Tibet. So these are the different potential mineral prospects and iron prospects I have shown to you in the location in the second location in the here in the second column, and the districts of these, their thickness, grades, and etc. is given. I don't have time to explain everything, but these are the location of iron deposits. Iron deposits, the main iron deposits out of. So these like this in Bajang, and this is Banglung, and this is our this Thoshe, this Phulchoki, and this Bukmanpur, and Chitwan, and this is in our Labdi Khola, and it is very famous one nowadays. This is in Nawalparashi, and I'll explain also. So these are the other places where we have some iron prospects. And the old mining activities before 1951, iron ore were extremely mined and locally smelted. People were fully dependent on their own indigenous production. But after 1951, finished iron was available in the market. As a result, people left all these difficult activities of mining and they are attracted in agriculture and other fields. So all mines were totally closed by 1964 due to change of the new government policy, difficulties faced in the mining at depth, as well as very much complex geology and lack of technical know-how. So at present, all required iron and steel have to be imported, 100%. Now myself, I did detailed investigation of Those iron deposits, rapid assessment of Phulchoki, Boda Pokhari, Tawari Pokhari, this very core, Lokorban and all these things, and then reviewed quite a few literature on this, and then we prepare, and this paper is based on that, on this report. Paper is based mainly in the field observation, lab investigation, literature review, and basic verification and metallurgical testing. So this is the Those iron deposit. This line about 200 kilometers northeast from Kathmandu at Those, Gogul, Gunda. And this new change now, BDC, before it was Those BDC, Ramesap. First export by Nepal Bureau of Mines, that is DMG, and later by private company, NGC Mineral Private Limited. Here, specular hematite is main ore with minor magnetite and traces of ilmenite, pyrrhotite, and pyrite. Two mineralized horizons, two different thickness, and so they are about traced in about 4 kilometers. And possible reserve was calculated preliminarily, that the geological reserve is 15.9 million ton with average 46.6 grade, including from 30% to 62%. So this is the panoramic view. Okay. So this geological map, here we have traced this mineralization belt from Arugote and up to the Singati. Very extensive trenching, and they're very well exposed, and they're old working. There are old working pits which I'll show you. There are almost more than 500 pits that are here along this, right? And not only that, in the Danga Digger and Sotre, there are also, we can trace mineralization and further is from Barampu to the Salini, they are all these. But this one is what I am talking about, all these. It's about 4 kilometers. So this is the iron ores, by trenching, and then we are taking the drainage channel samples. And then these are the ores, these old pits, and these are the exposure. And the old, in those days, locally people have smelted this iron and then prepared tripods and even the chain of the bridge. So these were the remnant of this gun factory. Here you can see all these things. They make 9 barrels of the guns. The tested 9 barrels of the gun has to be submitted to the military in those days. So that's why. And these are the old working pits you can see. So beneficiation advocated, beneficiation by simple crossing and washing with running water able to upgrade up to 62%. That is what I did myself, okay? And the loss was about 20 to 25%. And by mechanical methods that was tried in NESL, this Mineral Development Corporation India, Hyderabad, and their according report that can be updated up to 63%. Okay, upgraded more than 62% iron is suitable for the sponge iron, where and the Nepal NGC Mineral, this private company, is trying to and is planning to produce sponge iron to supply running the rolling mills and iron steel industries, whereas raw hematite for the cement industry, paint and other allied industries. Okay, this is the second one, the Phulchoki one. I will 2-3 describe because it depends on time how much I can give. So Phulchoki iron deposit, another good deposits, is located about 26 kilometers. Is very southeast part of Kathmandu, very close, and the mineralization band is stated here. If you see the lithography, and this is the test mining this tunnel, about 50 meters, still exists. You can go there, and then there is iron ore. So this by extensive geological mapping and distancing, fitting, as well as editing and some drilling, the mineralized horizon that has been traced like this, and by cross-cut and all this thing, and then that was 4.5 to 22 meter thick and 1 kilometer long, and that calculated about 10.67 million tons economic deposit, average grade 56.1. That is included. The proved deposit and the possible deposit also is included in 10.6. And feasibility study was conducted and the production of 103,000 ton of sponge iron. Similarly, small steel industry with 50,000 tons of its capacity. And this is the chemical analysis results. And the third prospect is Dhawadi, Pokhari, Durlung, and prospects. This Neval Prashi is one of the largest known iron this prospect known in Nepal. This lies about 108 to 228 kilometers southwest of Kathmandu in Neval Prashi district, and extension about 8 kilometers and a thickness 70 to 25 meters. So this average grade is around 50. And then since it is a ulitic hematite, and this is exposure, I can show you in next slides. So, sorry. This is the Permian to Eocene historical group of rocks, the Melpanic formation. Within this ferroquartzite, ferrogenous quartzite, sandstone belt, there is a hematite belt, as I have to you. Now, this is the formation, yellow color, and they extensively by trenching, pitting, etc. The hematite belt was traced. And recently they did Department of Mines and Geology, they did 2-3 holes here, and these people are involved, Pokharel and Baskota, and they prepared all these things. This all contribution, not mines, okay? The BMG contribution. This lower hematite zone, the upper hematite, there is in between some quartzitic and some these beds of shell and quartzite. So you can see very clearly, this is the road cut section, where you see this section totally clearly very fresh cut, okay? This fresh cut section, and this is ore sample, and then this recently the Baskota and his team departments, and then drilling was in Pokhari, and these are the core samples. And still he said he had not got the final result of the core. So I can give you that. And the other one is important, this Latikola iron prospect in Tadao district. So in the Latikola area, Latikola area, because if you try to continue tracing, then you can trace in Lister Kola, even Bhuth Kola. But the thickness is quite different in different places, as you see here. And then beside that, in Tadau, we have other prospects also in Gairal as well as in Kiran Kola. So this is the geological map, and then this is Lugdi Kola, this is Bhuth Kola cover, very famous old one. And then bend continued up, even you can trace here, but thickness is quite small, but it goes further east. So this is the exposure in the Lugdi Kola. You can see our students, they have work over here many times. We take them feel very easy in this place, and our friends, Mr. Khadka, he did this map, and this for his photograph I kept it here from this Chaukarirada, where that was mined before. And this Pradhan, this very long time before, our senior colleague Pradhan has roughly estimated about 7.5 million ton of. Now I go in short because in the detail I can go because of time, so I shorten this. So like in Bangalore, we have got the ready core, say almost 80%, and the thickness and the percentage is given. And then this Lakurban area, and then this Palakharka, Dhamja, similarly in Parbat district, similarly Gulbi districts. And so I'll send you few slides here in the Bangalore, Edikori area. There are two mineralization band. This upper one is 4 meter thick, lower one is 6 to 8 meter thick. And this is what we have traced roughly, these two mineralization bands in this area. And then in Lukurban section also, this is Lukurban Kola, we have the very clear cut two bands, upper one 4 to 5 meter thick and 3 to 4 meter thick. and there is a collapse, old workings in this Dugarban area. And now the other imported is Japan, this is Kachali, Ekgar, Patauri and Bhatgaon area, and possibly in the Bajang district, far western Nepal. And we have divided into two, the three prospects in western block and eastern block. We didn't have much data because people have not done in detail. So our colleague, he had mapped it like this. And then anyway, this we can see the starting from the 2.1 to 15 meter thick band iron ore is exposed, but the very initial work that has been done either. Similarly, in Baitadi area also there are two license in this Bajang area. These are the old mineralized bed like this, and then people would selected iron ore used to fit for the smelting, and then this is the pig iron they produced. So another Jalwang iron prospect in Rolpa districts, and then iron contained in some of ores in the Lungri Khola, Pagan Khola, and another Khola. That's our colleague, Mr. Joshi is here. He has mentioned up to 65.6% of this float in this float. So several old workings are also located in. Similarly,
can you conclude now?
I will conclude just now. There's 2-3 places like this we have in other districts also. So prospective mining license, Nepalese individuals or company or foreign company, they are registered in Department of Industry, and so they can obtain the license, mining as a thing. And also this investment holdings private limited and other African trade, South Africa, 3-4 Chinese and 2-3 Indian companies, like including the Vandana Global Limited, were interested to invest in this, but they are not successful. So foreign mining companies and investors had also shown their interest to invest in industry $11.5 billion in this sector in the concluding session of Nepal Investment Summit last year. So that has not been won. So now about the situation, there is a mining license. I will talk about only about in 2015, 16, 29 producing license. Now in after 1 year, only 8 were validated, and 3 in mining license, and only 2 are validated. So proportion. So in spite of interest shown by the foreign companies, as I told you before, Nepal is a net importer of iron and steel. All the raw materials required for iron and steel that has to be imported from the foreign countries. Annual consumption is, I told you before, about 10 million tons. And before conclusion, I have one slide. This is a situation of Nepal's annual total iron and steel import. The share of 10 major in space. If you see these 10 metal, 10 items, then you see in 12, 13, there were about 100, this one for petroleum is the first, the second was iron. So 16% of the total these imports, and then here now at about 103.7 billion rupees expended only to import iron and steel goods. Look, and that is whole import of the 22%, 19% of the whole import budget. Look the situation. Now I concluded, iron ore is known from 9 to, I told you, this I don't try to repeat it. Follow up a detailed exploration are recommended to prove the ore reserve and confirm the grade more precisely and all major prospects. Exploration and utilization of old mineral resources will generate employment, reduce the import, contribute substantially in the trade deficit and the balance, and save the foreign currency and overall increase in the national GDP. So there is a high chance to find out deposits in the other parts of Nepal, and government Nepal should give high priority to realize such resources and invite potential investors to invest in mineral mining industry sector so that our own mineral resources can be utilized. Sustainable development of the mineral resources and establishment of mineral-based industry play vital roles. Now the last slide is government Nepal should realize the fact, understand the importance of minerals-based industry and include it in the national program with highest priority, and give priority to mining of already known economic deposits and explore the explored the areas, the lesser Himalaya, unexplored Himalaya, and the virgin areas, the higher Himalayas. This last sentence, mining is a very, very risky and long-term period business. Therefore, the government Nepal must give some incentive like the tax holidays for a few years and made some amendment in existing controversy clauses in the Mines and Mineral Act, and rules and regulations to attract this potential investors. Thank you very much.
The next speaker is Samjawar Bhattacharya. He will speak on the glaciers and glacial lakes of Nepal in the context of the climate change.
I'm taking you on the surface of the geology or surface of the ground. That means the glaciers, glacial lakes of Nepal in the context of climate change. These glaciers and glacial lakes are not constant like as geology, whatever you have seen in the previous presentation. These are dynamic. We had mapped glacier and glacial lakes of Nepal and Indus Himalayan region in different time. But all the time, the number and area of those glaciers and glacial lakes are different. That's why if any one of you has to refer the number of glaciers and glacial lakes in Nepal as well as in the Indus Himalayan region, please refer the recent one. Otherwise, everybody will be confused because all the time the number and area will be different. This one of my colleagues is here, Sudan Vikas Marjan is over there. So in the abstract, I have given the co-author Sudan Vikas Marjan and Finos West. We are very small in team, though we are trying our best to produce the maximum area which we can cover to map the glaciers and glacial lakes of Nepal. As the geology, it's very difficult to map in the higher elevation due to the harsh climatic condition, rugged terrain, and very expensive due to the remoteness. So the same thing, it happens in the glacier and glacial lakes. All those glaciers and glacial lakes are above 3,400 meters above sea level. So it's not easy to map the glaciers and glacial lakes in the field. Ultimately, we have to be dependent on the remote sensing. But whatever it is mapped in the previous literature or previous report, those are mostly based on the topographic maps, some aerial photographs, but due to the technology, those maps slightly due to the projection parameter, we cannot use for the monitoring purpose or we cannot use for the analytical purpose. Whatever the maps, it was mapped in the previous literature or previous study, it cannot be overlaid on the recent projection pattern. But whatever right now you had, the Google or the satellite image, now all those are very nicely projected, and whatever you do in the Google or image, you can overlay on the existing satellite image right now, but not 5 years back. So due to these limitations, we had to work on the topographic map also. There are a lot of error in the topographic map. It's extremely high. So we had covered for Nepal, mostly we had Kosi, Gandaki and Karnali. Some around 35% Kosi catchment is in China part. For the glacier, not for the lower belt. Lower belt we had the catchment area in India as well. But we have not considered that one. We had considered only for the upper part for glacier and glacial lakes. The Kosi basin has some around 35% catchment in China. This is a transboundary, whatever the glaciers and glacial lakes melt over or flash flood, it will come down to Nepal. That's why we had mapped that area as well. And some part in the Kali River, Mahakali River, some section is a transboundary with India as well. So altogether the area is 176,000 square kilometers. So it's a huge area and mostly in the high altitude. So this is the latest data for the glacier and glacier lakes. Previously it was different. And this one, the number of glaciers is 3,808. This one is published in 2014. This is the latest one. And area of glacier is 3,902 square kilometers. That means the average area is slightly higher than 1 square kilometer. The number of glacial lakes is 2,070, but only in Nepal. If we consider the transboundary area to Nepal, then the number of glacial lakes will be 3,236. Sorry, 3,234, 34 or 24, something like. And potentially dangerous glacial lakes only in Nepal is 21. But if we consider the transboundary, then it will be 47. So altogether 47, and transboundary it is 26. One in India, in the Mahakali River, and 25 in the China. If it goes out, then it will pass down to Nepal. That means for the hydropower, it's very important not only to look inside Nepal, it is equally important to do the mapping and the analysis to the transboundary area as well. So as I had already mentioned that these glacier and glacial lakes are dynamic. So in the context of climate change, these glaciers and glacial lakes are changing rapidly. So if we say climate change, these glaciers and glacial lakes are very much critically sensitized by temperature change and the precipitation. So these two most important parts are the glacier. But other parameters as well, but we have not considered those parameters till yet because we are still in the preliminary stage. So from the IPCC report, the average temperature rise in 100 years was just 0.75 degrees centigrade in 100 years. But in Nepal, if we see, it was 0.15 to 0.6 per decade, only in 10 years, because we don't have data. Based on the 30-35 years data we had analyzed, per decade the temperature rise was 0.15 to 0.6. That means 2 to 8 times higher than the global average temperature. So whatever the temperature expectation it will be given by IPCC or international experts, then that will be higher for the Nepal. And even in the high altitude, that will be again higher. So IPCC is expecting 1.5 to 2 degrees centigrade to 3 to 4 degrees centigrade by 2100. But for Nepal case, it will be more higher. If the temperature and pressure, or if temperature and precipitation will be changed, then the ultimate impact will be glaciers melting and lakes are forming or expanding. So this is data from the Department of Hydrology and Meteorology. They had published the data in 2014 as well as 2017, but 2014 I have not considered here because that one is based on 30 years. And in 2017, they have given 44 years data to see the temperature, and here they have given altogether 0.056 degree centigrade per year increase. So this one is in Nepal, but if we consider by the physiographic zones or in high Himalaya, it will be 0.86. That means it will be higher in the higher Himalaya. And the precipitation is decreasing by 1.46 millimeter per year. That means the temperature is rising, glaciers are melting faster. In the meantime, the precipitation is decreasing. That means the nourishment or for the development of glacier, then it is decreasing in both sides. Income is also decreasing as well as expenditure is high. That means the resources or the source of the glaciers, whatever we had, it is decreasing. So during 2014, we had analyzed in the two specific glacial basins in the Langtang Valley and Imda Valley, where most of the glaciers are studied. Here we found the data from 1988 to 2008. The temperature data is from Department of Hydrology and Meteorology, and the decadal is the average temperature 1988 to 1997 it was 3.3, but 1998 to 2007 the average temperature was 5. That means the difference is 1.7 within 1 decade. Here also the temperature rise was 0.3 degree as well as 0.7, minus 0.3, 0.7, that means 1 degree difference. So we found the average temperature rise per decade was 1.7. Very rapidly, very fast. This temperature is rising in the higher Himalaya. In the Imda Valley, it was temperature rise by 1 degree centigrade in 1 decade. So at the meantime, the glacial area has decreased from 171 to 152, then 142, similarly 53 to 51, 45. That means the glacial area loss was 17% within 10 years. Here we had 15% glacial area loss in Imda Valley. Those glacial loss means there might have either the surface runoff will be higher or those melted water might be ponded somewhere. So from here, this is one of the examples of the glaciers in 1956. The scenario of the glacier in 1956, this one is the Imda, full of the valley. In 1956, the same repeat photograph in 2006, you can see the loss of the glacial mass. Not only the glacial area lost at the surface, even there is a formation of a huge lake. And this lake is almost 2 kilometers, more than 2 kilometers long and 600 meters wide. And the latest information, publication from Lala et al., the maximum depth of the lake was 157 meters, mean depth was 65 meters, and total volume of water will be 88 million cubic meters. This one is before the reduction of the water level of the Imda. But I think this value is a little bit higher, very much high, because the Choralpa, which is 3.2 kilometers long, and the maximum depth is 132 meters, and width is around 600 meters. There we had 75 million cubic meters of water. And that one is a little bit long one. But I don't know, this depth 157 is too high. Anyway, the scenario is like this. Glaciers, we are losing the ice mass. Those ice mass, those are the freshwater resources in the form of solid water. It's a reservoir, solid water reservoir. It is decreasing. In the meantime, those are in the formation of the big lakes, huge lakes. If those lakes outburst, because those lakes are dammed by the loose moraine, it can breach by any means. If it breaches out, then the structure or any development activities along the river in the mountain community, all it will be washed out. That means not only the resources of fresh water, we are having the development of the hazard in our overhead as well. So we had mapped the glacial lake. This one is the latest and still not published. It will be published soon. This one is the area where we had mapped the glaciers and glacial lakes of Kosi, Gandaki and Karnali. Karnali and the Mahakali part is a little bit in the India part as well, and mostly in the, and altogether we had mapped 3,624 glacial lakes, and only in Nepal we had 2,070 glacial lakes. So once we had mapped the glaciers and glacial lakes, and we tried to find out the hazard level or the risk from those danger glacial lakes. So that those lakes which are dammed by the moraine, they might be very much vulnerable to outburst. So we try to find out the stability of the lake based on either the lake will be the stable, it depends on the characteristic of the glacial lake, or it depends on the dam condition. If a dam condition is strong, good, then the lake will be stable. If the lake is growing very fast and erosional activity is very rapidly doing, then it will burst out. That means it depends on the glacial lake and the dam, that will be the stability of the glacial lake. Not only it is depending on the glacial lake and the dam condition. This will be impacted by the mother glacier as well. Mother glacier means those main glacier which is feeding to the glacial lake. It depends on the characteristic feature of the mother glacier as well. Not only this one mother glacier, another feature is the physical condition of the surroundings. Most of the gulf, it happened in Nepal and China. It was due to the avalanching or landslide at the lake. The mass which fell down or which was landed on the lake, and due to the splash of the lake or breakage of the moraine, then the gulf happened. That's why the most important is not only the characteristics of the glacial lake, dam condition, we have to take care of the mother glacier as well as the surrounding condition. These four parameters are very much important to analyze whether those lakes are really in the danger condition or not. Besides that, another big factor are the outpeak, which is difficult to consider in our study. Another one is the extreme climatic conditions, very heavy precipitation in the lake area or in the dam area. It can reach out, it can break that dam. Another one is the anthropogenic, because these water are the resources. So any activity mishandled or wrongly handled to use those water, it can reach or it can trigger the.
Can you summarize them, please?
Yes. So we have not considered this one, and on this four part we had made the dangers. These are all the details. For these four parameters, those detailed parameters we had considered to identify whether that lake will be in the danger condition or not. So on this basis, these three not considered, on these three bases we had identified 47 potentially dangerous glacial lakes. So using the GIS, we use all those filtering, lake size and type. I'm not going in detail. Ultimately, we had identified 47. Out of these 47, 21 is in Nepal, 25 is in Tibet, 1 in India, which comes along the Mahakali River, and in Kamor, all details we had. So most of the potentially dangerous glacial lakes which may burst out due to the different parameter, mostly concentrated in this coast basin, and very few in the western part. So once we had the potentially dangerous glacial lakes, then we had analyzed the danger level of those lakes, and we had ranked 1, 2, 3 ranked, and at the same time, based on the existing hydropower or potential hydropower, development of hydropower, community infrastructure, we did the risk as well, rank and risk. 3 rank, 1, 2, 3 vulnerability rank, and 1, 2, 3 risk. Then we analyzed and we found 6 lakes in the first priority. That means it's a high danger and high risk. So 6 in Nepal and 11 in China. Those 11 in China, if it bursts out, it comes down through Nepal to India. And the second is Nepal 7, China 3, India 1. The third category 6, 10, and the fourth category Nepal 2. That means we had all the information about the glaciers and glacial lakes. Then ultimately we found that in the context of the climate change, what's happening? That means the glaciers are shrinking and the lakes are expanding. Another one is those glaciers and glacial lakes are not only the resources of fresh water, but they are the sources of hazard for the mountain community as well. We have to pay attention in this way. So it is dynamic due to the climate change, so the danger level may change in the glaciers in the coming year. So every 5 years we have to make some type of inventory of detail for the entire area, and those we had identified the danger one, we should do detailed field investigation before reducing the water level or mitigating the risk for those lakes. And all those informations we had already published. Besides this, there are other publications as well under my authorship and co-authorship. All those documents you can get from this website. All those publications are online. Only those recently unpublished data, those are not there, but all other publications you can find here. And for the policymaker, planner, they can go to the Geo portal where you can see the applications, easy for understanding. And those for the researchers, those who want to do further research, they can get all those data sets in this website. And if any problem, you can contact me in this email address. So there will be no problem for the further research. And these data are very much crucial for the hydropower. Thank you.
What is the plan of mitigation for this flood?
Mitigation means to reduce the risk level. We cannot do properly. Till now in Nepal, we had lowered the lake, 2 lakes, Sorolpa and Imra. Similarly in Bhutan also, 2 lakes have been reduced the water level, as well as in China also 2 lakes. That means those lakes are such a huge one. If we do something wrong, then it can burst out. It had already happened in the Peru. So very carefully we have to reduce the water level. Either we have to reduce the water level or we have to strengthen the dam. Either the dam is strong, then we can reduce the risk, or we have to reduce the water level. Another one important information is we had all those information and analysis based on the remote sensing and GIS. So further analysis is whatever we had identified, those 47 glacial lakes are dangerous. All those lakes should be glove simulation. We have to do modeling. What will be the impact if those lakes burst out? What will be the effect or damaging intensity in those basins to what level? We have to identify all those things. Based on that one, then we can see the mitigation measures along downstream.
Deepak Chamlagan and others.
Seismic hazard and other related topics. However, the uncertainty inherited on those type of maps are still in discussion. So today I am going to discuss about the uncertainty that are inherited in probabilistic seismic hazard that we are doing especially for the Himalayan region. Look at this map. We have here 3 sets of maps recently published, and these hazard maps are for 10% accidents in 50 years. 10% accidents in 50 years is 3 maps. If you look at in detail in this map, first of all, Thapayan 1, they published in 2013. The high hazard zone or the higher peak ground acceleration are concentrated to extreme part of the world, east and west. And another paper, Raman et al., 2017, so they also found high hazard zone east and western part of Nepal, but different depth. If you check here, this maximum peak ground acceleration is 0.625, and for this one is 0.87. And for this one, the recently published by Stephen et al. In 2018. So in this paper, the maximum peak ground acceleration is 1.25. for the same region, the same geology, the same tectonics, but the values are different. And which one is correct? So it's really difficult to answer which hazard map is correct. So this is the motivation for this research. So in this all type of research, they adopted a probabilistic seismic hazard assessment. And there are two types of uncertainty in this type of research. First one is epistemic. In this, model parameters that one could in principle know all the parameters, but in practically these parameters are not known. And the second one is aleatory, that is related to some statistical analysis of hazard. So that is why in this research, I would like to focus on uncertainty estimation in seismic hazard for central Nepal. And this is the well-known figure by Roger Dillon. You can see so many devastating, great, giant, or moderate earthquake in Nepal in different times. You can see here blue patches. These are the rupture area considered for all those earthquakes. And the Gorkha earthquake is, the epicenter was located somewhere here and is terminated the Sindhu also somewhere here. So I consider the section through the central Nepal, which is roughly this one, with the well-known cross-section for this one. And if you say here, the main fault systems that are in these sections are main frontal thrust, main boundary thrust, main central thrust, SCDS, and synchrosuture zone. And these all faults are merged with the basal decollement that is called main Himalayan thrust. So this is the structural section we obtained for the north-south section. And if you go check the geophysical section, so here two profiles are merged, and this one is for by in-depthing by the seismic survey, and this one is from magnetotelluric survey, and this also shows the presence of main Himalayan thrust somewhere this part. It clearly shows, but this main Himalayan thrust mainly control the seismicity in this region. It is a well-known fact, but how, when it controls the seismicity, we don't know yet clearly. So here, these are the microseismicity here associated with this, and most of these all giant, big, or moderate earthquake are due to slip along the main Himalayan thrust. It is a well-known fact. So, if you see the rupture of this main Himalayan thrust during the moderate or the big earthquake or the giant earthquake, we have the different scenario. So this is the well compiled by Munier et al. In 2030. For example, if you talk about the western Nepal, the western Himalayan earthquake of 1505, this kind of rupture along the main Himalayan thrust occurred. That is whole system that is ran to upper surface, or the MFT whole part is ruptured during this earthquake. And during the great earthquake like 1934 PR Nepal earthquake, this right from the transition between the right from the rank to the south of the Himalayan front, entire fault is ruptured during this earthquake. And another type is blind rupture, rank. This upper flat. This upper flat only rupture. This is almost similar with the 2015 Gorkha earthquake, this type of rupture. And similar to the blind rupture, and sometimes these earthquakes also reactivated some of the other faults like acidity, and sometimes the duplex structures is ruptured, and similarly only the southern flat to the surface is ruptured. So these are the different scenario ruptures that produced by the different type of earthquake. So this means there is no consistency in the rupture development during the moderate to big earthquake in the Himalaya. And this is the Gorkha earthquake, that's the tectonics. The Gorkha earthquake originated at the hinge of the main Himalayan thrust. So from this data, it is clear that the main seismospheric source for the seismic hazard in Nepal or the Himalaya is main Himalayan thrust. And let's come to this cross-section that were prepared after the Gorkha earthquake. There are two interesting papers. One is published in Nature Geoscience by Elliott et al. In 2016, another is Hubbard et al. So these cross-sections are for central Nepal, from the same latitude, but the different structure. Which one is correct? First one, it shows the single rack here, and the rupture is somewhere from here in the ramp section, this Gorkha rupture. And the second cross-section you can see, here is only one mid-cluster ramp at the depth of like 25 kilometers here. But here we can see the two different ramps. One is the deeper ramp, so that is, it's a geometry also different, and another is just below the Kathmandu, they proposed another ramp that dips around 26 degrees, but this is 2160. So this means for the same region, we have the two different cross-sections with the different geometry. So what is the contribution of these geometrical differences on that? And we don't know which one is true for the same region. And if you consider the geodetic observation throughout the Himalaya, you can see here in the western Himalaya is about 13.3 plus minus 1.7 millimeter per year. But if you go to the eastern part of the Himalaya, this convergence, the slip along the main Himalayan thrust increases. That is, goes up to 21 plus minus 2.0. For the Nepal, especially for central Nepal, the convergence or the slip along the main Himalayan thrust is about 19.4 plus minus 1.4. So how this plus minus will affect the computation of seismic hazard? And if you look at the historical earthquake, so it has different characteristics. The first one is for 1100 AD earthquake. The rupture length is 280 to 400 kilometers. And similarly for 1255, 300 to 400. And similarly, you can see the great variation of rupture length in this part. And if you consider about the slip along the main Himalayan thrust, that is, you see for the 1100 is 9 to 18 meters, for the 1255, 6 to 12 meters. And if you see here, the great variation of the slip along the main Himalayan thrust. And even in the magnitude also, there is no uniformity. So this means for hazard assessment, what values could be the more realistic? And recently, after the Gorkha earthquake, we dug some trenches in the Himalayan front of Nepal. So these are some of the logs I would like to show here. So this trench we dug in the eastern part of Nepal. So this earthquake event is dated in between like 1146 to 1256 AD. And the slip is about, you can see here, slip is about 11 meters in this. And similarly, in the central Nepal, we dug another trench in Navalparasi in central Nepal. The slip is about 7 meters here. You can see the rupture zone here, Portland, is about 7 meters. So from these discussions, now we have identified some of the uncertainty parameters. See, first one is geometry and extent of MST. While you do the seismic hazard mapping, so how will you quantify or they develop the geometry of the MST and their extent too. And similarly, the magnitude of earthquakes expected on the MST. So what will be the size of the next overdue event? And then amount of slip on the MST expected during the large earthquake. What will be the slip along the MST in the next earthquake? Similarly, the slip rate of the MST and quite short ground motion prediction equation. I have shown in the second slide different hazard map. So they use the different type of ground motion prediction equation. So for the Himalayan region, unfortunately, we don't have any ground motion prediction equation. So that is why this kind of error is very common. And another is shear wave velocity of shallow basin sediment, like S30, G1 and G2.5. So these are some of the uncertainty parameters that we must consider in seismic hazard mapping. So taking these 8 parameters, we try to quantify the epistemic uncertainty along epistemic uncertainty due to the main Himalayan thrust in seismic hazard assessment. So these are the sites. This is the section we are taking, and if you see the cross section, these are like this. These are the triangles, so the different sites that we calculated seismic peak ground resolution for that region. For example, these sites are chosen very carefully, and it covers all the tectonic setting of the Himalaya. These Birgans and this Chimera is for the Gangetic Plain, Indo-Gangetic Plain, and Hetonda and Bharatpur, that is the Dun Valley. And after that, and we choose the Kathmandu, Pokhara, and Banepa, that is the Intermountain Basin. And to the north, we choose Chautara, which is just above the mid-coastal range on outcropping bedrock. So these are the sites we have chosen for this analysis. And now to quantify the geometry of the main Himalayan thrust. So we consider both models because we have two models. One is single ramp, another is double ramp. So we choose both is a moderate ramp and deeper ramp based on the Eloyd et al. And the Hubbard et al. And these are the geometrical features. It's the deep of the ramp and the flat and the width of the fault. And this is magnitude. So we don't have the uniformity and we don't know what exactly would be the next earthquake magnitude. That is why we use the Leonard 2010 and 2014 scaling laws to calculate the maximum magnitude for rupture of 200, 400 and 800 kilometers. So we had three values: minimum of maximum earthquake, and the median, and the highest maximum earthquake. That means three values. So this is the value shown by this asterisk is the preferred value for the seismic hazard computation. And similarly, sitting along the main Himalayan thrust, we calculated in this, and T average is the preferred value for us. And similarly, recurrence interval based on the geodesic data, that's 19.4 plus minus 1.2. On that basis, we have calculated the recurrence interval for the maximum magnitude earthquake. So these are the recurrence interval, and we use this 400 kilometer of rupture data for the computation.
Can you conclude now? Sorry, please can you conclude now?
Okay, so, and this is the different parameters we consider: maximum magnitude, sleep rate, and this is the logic tree. Actually, this logic tree provides the good platform to analyze those hazards. And this is the statistical approach. I don't like to go in detail. And this is the hazard map calculated for hazard curve calculated for the Kathmandu. Altogether, based on this logic tree, we have calculated 21,870 hazard curve for the region. And now let's come to the uncertainty analysis. And we plot the tornado plots for this one. And you can see here for the Chautara, this ground motion, contribution of ground motion equation, max, sleep, hot geometry, BS30 and sleep rate. How much uncertainty it provides. So CMP is the most important parameter that influence uncertainty in Chautara. Similarly, for the intermediate basin, Pokhara, Kathmandu and Banepa, BS30 is very important, and GMP is another important parameter to contribute highest level of uncertainty in seismic hazard map. Similarly, in Dun Valley, Hetonda and Bharatpur, GMP and BS30 and partly this fault geometry also contribute uncertainty in that region. And for the football site, like Birgans and Chimera, so GMP and BS30 is most influential parameter while we compute the seismic hazard in the region. And we also consider both single and double ramp model. So whatever the geometry, single or double, it doesn't have much more influence. That is same kind of influence parameter we got for this region. Now I'd like to conclude my talk. In conclusion, most influencing parameter for the seismic hazard assessment in bedrock site or the outcropping bedrock site is GMP and maximum magnitude earthquake. And for the intermountain basin, BS30, because shear wave velocity is directly affect the amplification on that region. So that is why BS30 LGM is important parameter for intermittent basin. Similarly for dune valleys, also GMP, ground motion prediction equation, and BS30 is important. And for the Indo-Gangetic plain, GMP, BS30 and MMAX is influential parameters. So from this, this conclusion suggests that in future, if you really want to do more realistic hazard assessment, we need to consider the further research. We must do on BS30 measurement, GMP, geometry of MST, historical earthquake, seismicity, and strong ground motion. I hope this kind of the conclusion can give way forward to carry out the seismic hazard assessment in Himalaya region. Thank you.
Very nice, interesting paper, lot of new information.
Providing token of love to our professor scientist, researcher scientist, senior scientist. May I invite Krishna Kafle sir.
To making some adjustments, so they have to take these papers for 12 minutes. I think this is enough. Okay, if authors will allow us. Okay, making any delay further, I would like to call first presenter, Mr. ASM Wabidullah from Bangladesh and his team, and his presentation, electrical resistivity survey in investigation of hydrogeological condition of Sialet, Sembarkar Hor area, Bangladesh.
Wabidullah, and I have a number of co-authors. I'm not going to the names of the persons because the time is limited, so I am directly going to present my paper, Electrical Resistivity Survey in the Investigation of Hydrogeological Condition of Silat, Sunamganj, Haor area, Bangladesh. Haor actually a depressed area where paddy is widely cultivated, and you will see Bangladesh is mainly rice eater country. We mainly rice, and we need huge. The Silat area, it is this area is in the north eastern part of Bangladesh, bordering India on the other side, Shillong part, and the area is shown here. This is a depressed area and a large area producing huge amount of rice from this area, and mainly we need some water in the for the paddy cultivation, and mainly in the dry season we need some irrigation water, which is mainly coming from the underground, or we are using groundwater for the cultivation of rice in the area. So that is why we are dealing with groundwater survey in that area. Actually the work is done for Institute of Water Modeling. They need some of the parameters for budgeting the water for sustainable development of groundwater for the irrigation as well as other purposes.
Element across it fault line. The slip surface may be parallel with the pollution plane and very frost and shared zone.
My presentation contains following project background, introduction, objective, tools and techniques, conclusion and acknowledgement. First of all, I would like to give some few brief about our research project. The project lasted for 4 years and it is still in process. And as we all know, the geoscientist knows, landslide is a product of cumulative effect. It cannot be justified with concerning with only one factor. So, Imperial College came up with a multidisciplinary approach covering landslide as a whole, including the social scientists, and it has eventually aims for the development of early warning system and low cost system in regards to the investigation to the geological workup. So we have selected one of the landslide in the Karnali Basin more specifically it's inside the Buriganga subbasin. This is a very large, huge mass that has effect more than 2 or 3 communities. So, in concern with the citizen science, also we have selected this landslide, and it is it can be seen here this car, and this is very progressive landslide. It's continuously advancing, so that communities who are in these bursts, they are continuously shifting away from the landslide.
This research is totally based on lab analysis, and for this lab analysis I collected river water sample and groundwater sample. The river includes 9 rivers, which is Vishnupati, Dobi, Manara. Isotope analysis is basically focus on oxygen and hydrogens. And we use cavity ringtone spectroscopy decarbonation for its analysis. The isotope value is reported in Paul-Formel deviations with respect to PS mode. And this is the formula for this analysis.
And then with these scenarios, we would like to map out the landslide risk on that area. So that is the overall research overview. To achieve this, we've gone through the way of using low-cost sensors to gather our data. And the reasoning behind that is in developing countries like Nepal, and with our topography, we really need a high-density network of rain gauges to actually get the scenario of the precipitation. So we've gone with the low-cost technology with our project here. We also plan to do intensity, frequency, duration curves for the study area, and based on that, we'll be hopefully we'll get a threshold for precipitation-induced landslides. So that is the reason why we're putting low-cost sensors and rain gauges in our area. Study site, as my colleagues already put light on the study site, it is in the far western region of Nepal. In Bazan and Bajra districts. So these are, this is the landslide, and these yellow dots are the gauges that we've put around our landslide to get the precipitation of that affects the landslide. Or the display we've put river level sensors on the outlet points of the streams that originate from the landslide.
First of all, I would like to welcome everyone, and today my presentation is actually a small part of my master thesis study, and the topic of my presentation is susceptibility mapping of earthquake-induced landslide using weight of evidence method in Haku, Raswa district, Nepal. Basically, I start with the introduction. In the introduction section, what is actually landslide is one of the major disasters which is responsible for many social and economic losses in Nepal, and it is as quoted by Dakar and Silva 2015, it is the second most lethal disaster in Nepal, and different authors have quoted earthquake that it is a trigger for other secondary hazards as well, and approximately around 430 people were killed and around 753 were injured according to the statistics presented by Ministry of Foreign Affairs after the 2015 Gorkha earthquake. And landslide susceptibility. Now, if I give the basic introduction of the topic, so susceptibility, what is susceptibility? It is actually the possibility of occurrence of a disaster, of a landslide disaster in a certain period of time based on local conditions. Somewhere here and to Mailung Govan in the south, and it covers an area of about 49.82 square kilometers, and the major drainage over here is Trishul Ganga River Basin. You can see this is where the Trishul Ganga River Basin flows.
Introducing into groundwater potential, protecting and conservation of the resource with sustainable use is a major aspect of the groundwater management. The delineation of groundwater potential zone is important to develop household purpose, irrigation system, and sustainable utilization. On the groundwater exploration standpoint, groundwater potential is the possibility of groundwater occurrence. Delineation of groundwater potential zone by using drilling, hydrogeological, geological and geophysical method is expensive and time consuming and also demands experienced people. While in this case, GIS and remote sensing is convenient and have been time saving as well. The major objective of the work is to summarize the recent progress, current practices and state of knowledge on the topic, and to provide a broader outlook on the topic, as well as to integrate the existing knowledge in different parts of the world in the region and practice adopted in the Nepalese context as well. That has been practiced internationally. Most of the work has been done in the arid to semi-arid region of the world. And in this case, I would like to skip the major part of the each work that I have reviewed, as explaining each and every work doesn't support the time. Or assigning the weight for each thematic layer. The mostly used method is the ASP, that is the analytical hierarchy process, that has been proposed by the SAT in 1980. It uses a pairwise comparison and depends on the judgment of the expert. For this, the different parameters will be compared using the matrix, in the matrix form, calculating the consistency index, random consistency index, and the consistency ratio. Generally, the consistency ratio less than 10 is accepted as acceptable inconsistency.
Partners with work packages 1, 2, 3, and 4. And today we had some presentations on rainfall package 1 and geology, engineering geology package 2. Others were unfortunately absent. The main idea behind this research was to go to a remote part of Nepal where earlier works are lacking or very few, and to choose quite large landslides so that we can get some understanding of the failure. So continue in coming 2 and 3 years. So our main target is to come up with some kind of early warning system. The idea of early warning system is a little bit different from conventionally we think here. We are not going to target individual landslides only. Of course, we are monitoring those landslides. We will see how they move, how fast or how deep they are, or their kind of damage or obstruction to the streams. Based on geology, soil type, land use, and other parameters, we should be able to see what kind of this precipitation will trigger the type of failure, or in the watershed. This kind of work is now being done in India. It will be somehow linked up with the precipitation and our geological, geotechnical information. That is our goal. And people will be warned of this problem beforehand. So that is the main idea. Of course, another landslide of Sunkuda, the landslide presented here was basically a rock slide. Main controlling factors are joints, as you can see, and weathering, deep weathering. But the other one is a soil slide, and also quite deep. So they both are quite large landslides, and we want to see the response of people, how they react and how they manage with the landslide, because it is a citizen science. So our one team, Work Package 3, is working with the people in the field. And we're also planning to do some training programs and coordinate with these local bodies as well as the government organizations related to the landslides. This is about our landslide eco project. And I think that in the future we will have more information and we'll be able to present in this kind of gathering. Thank you.
Nepal Geological Society providing me such a great opportunity to co-chair with the Professor Kazuki Koketsu. And let's have a big round of applause for Professor.
Thank you very much. Thank you, Professor Koketsu and Ms. Monica Jha for chairing and co-chairing the sessions. So it's my pleasure to hand over a small token of token of love to our Professor Koketsu, chair and co-chair, and of course the reporter. So can you please?
These are the results. The first, let's talk about the quality assessment of water and sediments. Talking about the individual parameters that we took, let's talk about the total dissolved solid. Total dissolved solid, TDS. As you can see how the TDS increased from as white Sundar dissolved, and it increased rapidly when we go to the downstream where the core of the cities lies. Similarly, dissolved oxygen, you can see the amount of oxygen from site 1 Sundar dissolved, how it dramatically decreased towards the site 10. So due to the low dissolved oxygen, we don't expect any aquatic environment to sustain them. Similarly, E. coli, which is a kind of bacteria that indicate the fecal and pollution in the water, you can see the amount, the value of E. coli is also tremendously increasing when we move towards downstream. Similarly, the total suspended solid is also increased from site 1 to site 10, and you can see how the value average is around this Thapathali and Tegu area, which can indicate that there is a contamination of hotspot around these Thapathali and Tegu sites. We get when we collectively interpret all the data, you can see the values we have collected is on this side, medium, which is somewhat acceptable, and it has tremendously, dramatically drops down on the bad, which is very unacceptable. The river is almost considered as bad because the values, the oxygen level, you can see is very low. So another results we did beside water sampling is analyzing of metals in the sediment, and this was done on the Department of Earth Science and University of Illinois. And for this, we use XRF spectrometer for analyzing. You can see the accumulation of metals in the Bhagmati sediment: arsenic, cobalt, chromium, copper, iron, nickel, lead, zinc. So why it is necessary to know about the presence of metal concentration? Because they can be they can show us that the water has been polluted. Also, the part 3 activities include the surveying of the people. Total 130 homes were surveyed during this project, and we conducted the homes along the Bhagmati River. We visited the neighborhoods. We interviewed the people about their health issues, aesthetics, and their use of Bhagmati River in the daily requirement. We also interviewed questions based on quantity of water they use, their distance from the river, their level of dependence, and also probable access to the alternate water sources, and also evidence of waterborne disease in the. You can see even the people, they use Bhagmati River during this washing.
My study area covers about 15 square kilometers, and it includes villages such as Giranchor, Dikuribesi, Bangapati, Baswari, Thakli, Chandala, and Chakadok. And the major rivers that drain my study area are Indravati River and Sindhupura. So that is the flow chart of applied metallurgy during my study. My study mainly involves literature review, secondary data collection, fieldwork, and data analysis and interpretation. Fieldwork was divided into 3 sections: geological survey, spring survey, and questionnaire survey. During the spring survey, the spring inventory was carried out, and then discharge was measured through the use of a volumetric method, and the land use nearby the springs and the type of deposit around the spring sites were also visually described. And for analysis of distribution of the springs, first, at the very beginning, topographic map was collected. It was georeferenced in GIS environment. It was processed in GIS environment, and then data on drainage, contour, and elevation were extracted that were further used in the preparation of DEM, slope, and stream density map. These maps were reclassified, and finally overlaid over spring inventory map, and analysis was performed. So now let's enter into results and discussion of my study. So let's get into geology. Geologically, my study area falls within higher Himalaya, and following Vietnam until 2002, it is covered by Talamarang Formation. So spring district springs, altogether 41 springs were observed during the field work in my study area. These included flowing as well as non-flowing. The ships were also, some of the wet areas were also included in among the 41 springs. The springs were coded from SP1 to SP41. In terms of slope aspect, I don't think it is of much of significance because there is no majority in any of the slope classes in any of the aspect classes, and the distribution is quite similar. Based on the classification system of Meander 1923, I have classified the springs my study area as 5th, 6th, and 7th magnitude springs.
Welcome back. Good afternoon. Now we are going to bring for a special session of National Reconstruction Authority, and it's my pleasure to invite Dr. Chandrabahadur Sestra, Honorable Executive Member of NRA, to chair the session. Similarly, I invite Dr. Rishiram Prajali to co-chair the session, also from NRA, Ms. Dharna Kamal and Ms. Goma Kharga as rapporteurs.
Pleasure and honor to chair this session. So we have team of my colleague co-chairpersons, the rapporteurs will be joining us, and panel discussion coordinator also Dr. managing this session. And this is 13:55, we are slightly late. So I would like to request all paper presenters to maintain time, and we will inform a bit ahead of time. We will do that before 5 minutes of the completion of time, and then we will give final notice, and then I would request to stop presentation there because the second presenter is not here. So, however, I would like to spare more time for discussion because in addition to the presentation, there is rich, experience around our audience. That's why I would like to allocate reasonably good time for discussion. That's why it is.
Good afternoon, everybody. I'm Naveen Paudil, a structural engineer, working as a district support engineer at NRA since 1 year. On behalf of our executive member, Dr. Rishiram Prajali from NRA, I'm going to present this presentation today. And the topics of the presentation is intervention for safer construction after 2015 Gorkha earthquake. Earthquake of 2015, there is a lot of damages and casualties that happened, and from the data, it was found almost 9,000 people are killed and more than 22,000 people are injured from this earthquake. First of all, to cope with this earthquake, National Reconstruction Authority did the damage assessment, and there are different damage grades from the technical point of view, and almost 10 lakhs houses are studied to find out the damage level. Third trans beneficiaries, we already the people getting the third trans, the number is 3,90,000, around 19,000 people, and the retributing beneficiary is around 61,000.
I'm from Department of Mines and Geology, and my talk is the skeletal triangle arrays for centrally circular array method for the long period microtumor in the Kathmandu Valley. Microtumors are classified into two types. Short period microtumor between 0.1 to 1 second or high frequency are mainly caused by human activities like traffic, industries, and their propagation characteristics provide the information about the shallow underground density structure. Likewise, long period microtumor are mainly caused by the natural cases, for example, oceanic waves, tidal waves, atmospheric pressure, etc. And these propagation characteristics provide the information about the deep underground cerebellum structure. So, our study concentrates in the Kathmandu Valley, mainly in the different geological environments, one in lacustrine sediments in Teku Kalimati area, one in DMG area, and another in Singhadarwar, where the administrative centers are concentrated. And as we know that the underground structure of the Kathmandu Valley is not even. So, the sediments have the big thickness, and it's very important to understand the underground cerebellum structure of the valley. So these are the instruments we use for the long-term microtumor. All the instruments are donated by JICA under the CENTES project in DMG, JICA and the University of Tokyo. So here mainly we do different trials in the methods between spatial auto-position method for the underground density structure, centralized circular array method for the irregular skeletal triangle, and seismic interferometry. So we apply all these methods in the Kathmandu Valley for the underground density structure.
Kiran Bala from the Northeast India, Manipur. My birthplace is Manipur, is in Northeast India. And we have done some projects regarding the earthquakes. And then just one simple case study we have taken. I do work with my PhD scholars and then our MTech students. And it was on 2016, and the identity on 26 January 2001, Bush earthquake was there. Then afterwards, the old experts of the engineers, scientists, geologists, all together discussed that we should have changed the codes. We have different codes for for different materials, for different buildings. We have different codes. Then this IS 1893 2002, previously also in 1962 they started this seismic code. But again review every 5 or 10 years we reviewed, and then according to that we are this interior red part is in Northeast India. Northeast India we call it 7 sisters. And except Sikkim is in zone 4 and Manipur is in zone 5. Because of the soft story, at the Kaisampat area, Kaisampat means is the 0 mile in Imphal. Imphal is the capital of Manipur. And then Naurengthong, these are this Kaisampat, and one residential building was damaged fully. It was 3-story building. And then it was Naurengthong is a part of the nearby inside the Imphal area, and the Dularen. So like the Dularen building, this building was also damaged.
This is the topic of my talk, and then the topic is probabilistic seismic analysis of Nepal, and then this was the work, and then this was by PhD work, and then I did with my advisor, Professor Omar. The southwestern part of Nepal, and then the value of ISPDA is exceeded 0.57, and then the lowest is less than 0.25. Similarly, for the 2% probability of accidents here, and then the highest, and then the lowest. And then in order to see the consistency of the result, it is also better to compare this result with the result of the previous and then the neighboring country, and then this is our map with the 10% probability, and then this is a national map of China, and then the prepared in 2001, and then the highest hazard. We can also see here in this region, and then similarly the trend is decreasing, and then similarly also we have also compared the other map with that of India, and then the jungle pattern is more or less same on this area and this area, and then there are also the differences on this area. So that how the major conclusion arrived was, we have just updated the earthquake catalog for this region, and then the based on the spatial distribution of earthquakes as well as fault, and then the tectonic information, we have just established 23 potential seismic sources for the Nepal, and then the seismic radar map showed that the highest ground motion was found just in the forestern and then the eastern part of Nepal, and then the lowest in the southern part of Nepal.
We all know that we fall in the earthquake-prone region. Strong earthquakes occur rarely, but they are very painful to the population as well as the economy of the nation. But earthquakes occur. They occurred in the past, they are occurring at present, and they will occur in the future also. These are some of the discussion earthquakes which happened in the past. This is the time of the 2015 World earthquake. That time the clock also stopped the function. So, as we cannot predict earthquakes, then we should rely on the result of seismic hazard assessment, so that the result could be incorporated in different sectors like policy making, planning, building design, retrofitting, and so on. There are two techniques for seismic hazard assessment. One is deterministic seismic hazard assessment, and the other is probabilistic seismic hazard. SSH is a dynamic process and should be revised periodically when new findings and new experience arrive.
Study of Kuala District Center of Nepal. It will be presented by Harish Gandhi and Paralympic.
Good afternoon, all of you. My name is Harish Gandhi, student of MSc Engineering on the campus. So this presentation is a part of my thesis research. So first, I would like to acknowledge my thesis supervisor, Dr. Tani Patrai. Secondly, I would like to acknowledge my friend Pushkar Bhandari, who came speak with me, and all my friends who are supporting me today. So the topic of my presentation is an approach of preparing earthquake-induced landslide hazard map of case study of Kunmapur district, Central Nepal. Diversity in topography, which of course has a lot to do with landslide. So the major objective of my research is to prepare an earthquake-induced landslide hazard map by using exact same methodology used by Saika project team to prepare hazard map of Sindhupal Chokha district and check either that methodology is applicable in Nuwako district or not, and then to convert a portion of map into an engineering geological map which can be used for designing linear infrastructures. So the methodology goes like this. First, data collection, satellite image interpretation and field survey to make a landslide distribution map, and then preliminary study on the existing hazard risk, and then identifying topographical and geological factors. After that, extraction of data structure was done, and then that was analyzed using quantification theory too, and then risk assessment score was given. And then major 4 factors were used: 2 intrinsic or topographical factor and 2 extrinsic factors. Intrinsic factors were slope inclination and slope aspect, whereas extrinsic factors were distance from the first and distance from the center. So first, the factors were classified and categorized, all the feature value ranging from 10 to 20 degree inclination were categorized as 2, and it was classified and categorized like a north, northeast, east with 1, 2, 3, 4. So it will help during giving the weightage during preparation.
Well, 2 papers were on earthquake engineering from civil engineering aspect, as you have seen. There we discuss, say, disaster handling, data collection, emergency measures, rehabilitation, reconstruction, local knowledge. I think today we are very lucky that we have Dr. Kiran Bala Dede with us, and we can share with her the experiences that they went through in 2016 Manipur earthquake. And as I have seen, it's very much similar to what we have done over here and what we went through. So, and besides that, I think we also have some local problems and local knowledges we can share with them as well, and with her paper, I can say that we are not much different. And then 3 papers on seismology. So 2 papers on PSHA, and it's basically from geological point of view. And finally, we have a very good paper at the end, which is earthquake-triggered landslide hazard mapping. And I think, to that, Harish could have added some of the measures that we should have taken for the future, or if we can extrapolate or interpolate whatever he has done for our future measures. That's what I think we could have discussed in the discussion time as well. So I thank you very much for the excellent papers, 2 from civil engineering, as I said, 4 from geology, of which 3 from seismology, and the last one, earthquake-triggered landslide hazard mapping. Thank you very much.
We are towards the concluding session, and from this conclusion, I again would like to invite Worship Dr. to say, would like to say something. I've said a lot. You have said a lot. Yeah. No, but thank you. Okay. Then I would like to request Dr. Nishiram Parajuli to make remarks actually, about your observation of papers as well as the questions that were raised, and if there are any other issues, questions which are not answered, and then if you think you are appropriately placed, you may also respond to them.
I would like to thank the organizer, NGS, for giving this opportunity to co-chair this session. It is actually special, not only in terms of NRA, but I think to bridging between the engineering geologists and seismologists to the engineers. There is a gap. I always say, there is a gap. We are talking about the even PSHA, and if we go for the structural engineers assembly, there we would just only talk about this point something deep, just a one gap. So, but we must have to understand the ground motion characteristics for the engineers, so that the geologists or engineering geologists, seismologists, they have to know this. So I always just talking about the damage scenario of this earthquake also. If we just look at the magnitude, then we have to expect many more damages. But why? Kathmandu is surviving. I have to say, it's surviving. Nothing happened. If all the structures constructed to follow the building codes as it is, none of the buildings have to damage severely. Just non-structural damages could have expected. So there is a gap, I think, and this session tried to fill the gap. So here, there is another question that raised to NRA. Actually, I am not the authorized person to answer it, but I think quite related, because I am working in the Srinagar retrofitting project, and I look the whole building. Just from the outside, what the general people see the building Srinagar and what the hooks was here, was severely damaged, but it was minor damage, structurally. Structurally, I am saying, structurally. And there are some other effects. If we talk about the material properties, that is the mud mortar structure. So the shear strength of mud mortar is very low, that anyone can manage. About the brick unit, I think no one can expect. When we tested the bricks, the minimum strength is 12 MPa and the maximum is 26 MPa. That means that stronger than M25 concrete. which is generally not used in common buildings. In common buildings, we used M15 to M20 concretes, but M25, almost like that. So it means the bricks are strong enough to withstand the compression loads and other, like mortar. For the mortar, we have to be careful about the shear strength, so we have to introduce intervention for the improvement of the shear action, like that. So for the retrofitting of the structures, in common structures, actually NRA has made a guideline, like there was already surveyed and fixed the damage grade of each structure. So for the damage grade up to minor of 3, those structures are supposed to be retrofitted, and other than are for the reconstruction. So, but actually most of the structures are of mud mortar, brick or stone and masonry. So I think there are some locally also the engineers will also evaluate the buildings and also can define the retrofitting or reconstruction. I think it's answer all the concerns. I'm not sure if you have any questions or anything. Okay.
We had to close this session by 10 past 16, which is 10 past 4 o'clock. It took a bit longer. Apology for that. Let me start my concluding remarks, not concluding actually, but some remarks over the presentation so far made. I am very much delighted, and I would like to also thank this Nepal Geological Society for dedicating this session for National Reconstruction Office. This is really very good privilege for us, and then also recognition and also potential collaboration between Nepal Geological Society and National Reconstruction Authority. For that, I am really thankful, and it is really thoughtful. Thank you very much. And with regard to the composition of papers, I am largely happy with the composition of paper, but it could have been further improved actually. In future, most probably, we may need to collaborate further, because if it is dedicated to NRA, then we could have presented more robust way actually. What is NRA doing? What are our experiences in terms of geological front that we could not explain, elaborate the way how we could have done. Most probably in future, while designing this type of program, I would really request you to organize that we can contribute more in robust way, more in elaborated way, fashion, so that it can be beneficial not only for NRA, because we will be receiving feedback from this very highly learned, individuals, professionals in your respective field, but also NRA will be benefited because you will receive a very much rich contribution from your side. So that is something, the lesson which we learned out of this. And with regard to the composition of paper, the first paper, you may have noticed that it was just about NRA's practice in some of the structural works. That was not, that is very much common, as we also learned from India. It is very much common because in response to the earthquake reconstruction process, more or less similar type of methodologies, construction technologies are adopted. And what is the Nepal specific? That we will need to still wait a bit because we are in the middle of the reconstruction phase, and we have to conclude the reconstruction phase. And by then, we will try to contribute to the old knowledge, or one body of knowledge, or one practical implication, policy level implication that I will communicate, that I would like to issue to this audience. The second is, NRA has been pondering, but we have not reached to one meaningful conclusion. The issue is this landslide, earthquake-triggered landslides. And there are majority of settlements which are not viable and physical. There are a number of settlements. And then the susceptibility of landslide and then earthquake-induced landslide is very, very much severe. and particularly that is true for northernmost districts, actually, like Rosua, Oahu, and also Gorkha, northern part of Gorkha, Dhading, as well as Ramechhap, Gorkha, like those districts actually. And we wanted, at the initial stage, we wanted to initiate some sort of integrated settlement program, but we encountered with another practical difficulties that these integrated settlements have also their own limitations, because the settlements are there because there is some sort of livelihood opportunities are also there. Unless livelihood, we could not provide livelihood opportunities, then it is not possible, it is not viable to initiate integrated settlement. Because of that reason, we didn't unfold largely aggressive type of settlement program. We are very, very much modest, and we have been adopting rather modest and then interventions in that front. One question is still unanswered. Maybe this geological society community will need to suggest. That is, how can we relocate those settlements which are not viable? They are not viable because of the slope characteristics, because of the stability characteristics. From all characteristics, there are a lot of settlements which are not viable. But what to do with those settlements, where to settle them down, is unanswered question. And then most probably, during this type of discourse, we will need to find appropriate answer, and we have to suggest to the government to adopt settlement policy. What is our settlement policy? What is our land use policy? That we have to speak. It is good idea where the earthquake-induced landslides take place, but what to do next? What are the way outs? It is also our responsibility to inform government that, okay, this is the problem and this is the potential way out. And there are different options. Most probably, we all will need to ponder on this, and then if we can come out with some indication and also alternative options, that will be really useful contribution to this country. All questions, I think, are addressed by the respective paper presenters. There was one question with regard to the NRA's policy on retrofitting. As my colleague mentioned that, minor grade, there are 5 grades for you. I think all of you are aware about that. There are 5 grades, 5 being highest severity of damage, and 1 being least severity of the damage. And then what we adopted policy is, in each grade there is minor and major grade. And in grade 3, there are minor as well as major grade. If grade 3 damage is there, and then if the category is major, then it goes to the reconstruction. If grade 3, if there is minor damage, then it goes to retrofitting. Similarly, grade 2 major damage, then it goes to retrofitting. And grade 2, but minor damage, then it goes, nothing, special intervention is required. That is how we have adopted our policy. And according to that, NRA has been supporting all earthquake victims. That is the aspect of the question. So, by all, actually, thank you very much for all paper presenters. It was very, very much useful event, and also contribution and patience, for your patience and listening until now, until the end of the program. I would like to thank paper presenters as well as audience, and then hope that this session you may have found useful. Thank you very much.
As the chairman closes the session, thank you very much, chair of the session, Dr. Chandra sir. I am the co-chair, Brazil sir. I am panel session coordinator, Professor Hikmat sir. So as the coordinator of this session and as the co-convener of the this 9th Nepal General Congress, I just want to give some small talk to our respective sirs. So please.
Welcome to this nice and interesting session about the geological mapping. I call the first speaker, Shiv Kumar Baskota, for the talk. The title is The Status of Geological Mapping in the Nepal Himalaya by Department of Mines and Geology.
I am Shiva Baskota from the Department of Mines and Geology.
presenting about the status of geological mapping done by Department of Mines and Geology. As the title reveals, this is not a research article. I am not presenting some outputs of the research, but I just want to show you what we have done so far from Department of Mines and Geology. In fact, it is in the form of white paper of the geological mapping section of Department of Mines and Geology. I presented it in the form of whole geological map of the whole Nepal and textbook as well. So there are other works from Bordet in 1961, Lustuliansa in 1964. So these are some works done before the establishment of the Geological Survey of Nepal. At that time, it was called Geological Survey Department. In 1967, when Geological Survey Department established in Nepal, then regular geological mapping and other exploration activities were conducted through the Geological Survey Department of Nepal. From 1976 onwards, we are conducting geological mapping through the Department of Mines and Geology. And we have mentioned here that during the 80s, UN-funded mineral exploration project was run in Nepal, and especially in the central Nepal, Lesser Himalaya, mineral exploration as well as geological mapping were performed through this project. So, a huge number of field works were carried out during 1969 to 1983 through mineral exploration project under the UNDP.
And risks of landslide, we know it can impact very seriously in terms of social, environmental, economic costs associated with the land use and development of any land policy. And in our country, many villages are situated on and adjacent to landslide. So this is the reason landslide risk is always a very important component in land use planning, because it plays the key role to demarcate the safe and unsafe area. During this reconstruction process after the 2015 Gorkha earthquake, majority of the discussion is going on how we can become safe and unsafe in terms of the landslide triggered by the this recent earthquake. It means 2015 Gorkha earthquake. So it is very important for any developing programs. And where are the risks? We are talking about the risks and where we can see the risks. And landslides are sparsely localized in steep slope of the river valleys, close proximity to the thrust fault, and boundary between the competent and incompetent rock strata. And we see this geological structure, basically the thrust fault, axis of anticline and syncline. These are the major factors which can cause the instability on either side, and therefore the proximity means how much the proximity we have to based on the field, and we have to calculate the proximity area so that that area belongs to the risk zone of landslide and for land use planning. It means when we see about the Google Earth, and you see the number of landslides very, very closely spaced, and on the adjacent side there is cultivated land, settlement area, and if we do not consider this kind of feature surrounding our land use, different types of land use, which I will talk later, and we cannot do the best land use planning. This is the reason we are very much focused the landslide risks. Not only the landslide risks, we have to talk at the multi-hazard risks, and today I discuss only the landslides, and therefore this is the very important concern for the land use planning.
These are the centralized location. From this location I have collected the samples for petrographic analysis. Main geological structure observed in my study is MCT, which passes through the boundary and through the area. And it is demarcated by the abrupt change in lithology from schist quartzites to the Lesser Himalaya to various gneisses in the north. of higher Himalaya, and it is demarcated by mineral grade from garnet grade mineralized garnet grade metamorphism in the lesser Himalaya to kyanite to stibnite grade metamorphism in the higher Himalaya. The sedimentation fault observed in paletic schist. This is outcrop scale fault and also fault, and this shows south version drag fault, and this is the isoclinal fold in Belden gneiss. Sincere. These are other structures, and this is the pulse to the foliation. The axis, the plot of axis of drag fold shows the mainly east-west trend, whereas the plot of axis of tight isoclinal fold shows north-south trend. This is the generalized plot of foliation of different parts of the map. Let's move on to petrography. The higher Himalaya includes the different gneisses. This is photomicrograph of kyanite gneiss. The photomicrograph of Belden gneiss. Talking about lesser Himalayan rocks.
Professor, call upon our past president, Mr. Uttamol Srestha, to present this token of to Mr. Professor Krosh. Please come up.
I'm going to present my paper entitled on some geological and lithological factor controlling river blocking by landslide. I want to thanks to the Nepal Electricity Authority for permitting my attendance, and I also like to acknowledge my all co-authors. So this is a summary of our continuing investigation. It's about geomechanical rock property related to lithology and rock weathering, landsliding, landslide permeability, river damming, and we have taken the two examples, one Jure landslide and another Langmare landslide. So Jure landslide is a monsoon trigger, deep-seated bedrock failure and damming of Potekose River, and Langmare landslide is a bedrock and glacier failure, impact into a glacial lake and superglacial moraine, a glacier lake outburst flood, debris flow, pre-blockage of Moron River, then a landslide dam, lake outburst flood. So river damming, landslide can cause upstream river impoundment, flooding and downstream flooding due to the sudden dam rupture. To dam a river, a landslide must be long enough to reach the river, voluminous enough at river level to abstract flow, fast enough that river flow does not continuously erode the landslide as it is added, low enough permeability that the dam retain water. So today's focus is on bedrock lithology and geological structure. So this slide shows the location of the Jure landslide, and it was occurred in August 2014. It is 70 km northeast of Kathmandu. 156 people were killed here. In this slide, we have shown the multiple small mass movement. We have taken the example from the Google Earth, which was in 17 February 2009. So in the next slide, we can see the 2013 landslide wake-up call, and it is also from the Google Earth of 12 February 2013. So here you can see the Jure landslide in occurred, and as we told before that Ornicut highway was buried, you can see in this image, and there is the impoundment of lake, landslide dam 55 km, and it was the image from 9 August 2014. This slide shows about the Jure landslide with lots of water seepages, and down is the water are the mixture got from the Jure landslide. So here we are talking about the material. Pore filling landslide is a low permeability mix of powder, cobbles, pebbles, sand, and cement. So we are going to say about bedrock, intermediate meta sandstone and schist with quartzite nodules. So in the right part you can see the water seepage. So this slide shows the bearing orientation and the number of joints.
Population growth and other development activities. Our country with many mountainous terrain has a tendency of increasing number of road construction, thereby formation of inevitable large-scale cut slope formation. the problems involving the slope stability has emerged as the major concern. Presently, unsystematic and unscientific cut slopes are being the source of slope failure. Slope cutting could be hazardous if not performed with design considering the geological issues, soil and rock properties. Inaccurate surface and subsurface exploration can result in the slope failure during or after the construction, thereby increasing the construction cost, delaying the construction severely, affecting the road traffic during the operation phase. Many times we get blocked in the traffic jams due to the slope failure problems. From the DMG, I mostly try to find out some of the problems during short visit of my field work along this section, starting from this Carton Valley up to the Tarai region. In many cases, this is the scenario of our roads. Though the rock is hard and its strength is very good, but due to this kind of shear zone or the wedges formed or structural cause, many big slides, rock slides and wedges failures get caused, due to which many times there is the roadway obstructions.